Okay, so we're going to be talking about high availability and clustering today. So let's just think about this idea of clustering and high availability generally. So we're talking about our gateway device here. So this is our connection to the outside world, and probably the connection between our internal networks as well. So it's quite likely that we'll have a number of internal networks, and the connectivity between them will be going through our gateway, and we'll be dividing those into zones and maybe setting up security between the different parts of our internal network as well. So in a business environment now, it is not that uncommon to have quite a good deal of your data, your servers, your infrastructure actually in the cloud. So we might have, so we've got a Windows environment, we might have our domain controllers on premises, we might have our data, our SQL servers, our other servers in a cloud. Maybe we've got a Microsoft Azure cloud service set up. Or maybe we've got some other kind of cloud service set up. So it's not unusual to rely on day-to-day business activities, or for day-to-day business activities to rely on access to cloud services. So in that situation, it is our gateway that's providing us with that connectivity, providing with that access to these services, which not uncommonly would be essential for the business to function at all. So you think about the role, the critical role that the gateway plays. It is something that we really can't afford to lose this. We really can't afford to have our gateway go down and not be functioning. And even though these devices I've found to be extremely reliable. In fact, I never had a Juniper gateway just die. But what I'm saying is, it's not impossible. Right? Things happen. It could certainly happen. So when you think about that, the business relies totally, in many cases, on this connectivity. I mean, even with our business here, our student management system is in the cloud. Our learning management system is in the cloud. We lost access to that. Well, we would be able to process enrollments. We would be able to look at students' work, the results, grade work, any of those things. So, as a training organisation, we are certainly reliant on an internet connection, but think of other businesses. Think of accounting firms, government departments, an airport, those types of organisations that are totally reliant on connectivity. So you can think, well, okay, it's absolutely essential that my gateway is up. So what solutions could you provide that would ensure that if a gateway failed, you would have the services up and running again as quickly as possible? We think, well, maybe I'll keep a spare one in the cupboard, and maybe I'll have one live hooked up, and I'll keep a spare one in the cupboard. And if my live one failed, I'll just brace up, pull it out of the cupboard, and bolt it into the rack, power it up, download my configuration, which I've got saved on my FTP server. Download that, and away we go, up and running. Well, yes, you could do that. You could do that. But think about a situation where that particular business is, say, a medium-sized accounting firm. Let's just say they've got 50 staff there, or 50 accountants that are working on client files. Some are junior accountants, some are senior accountants. But let's say on average, their charge out rate is, say, $200 an hour. Okay, it's not not extreme. That's probably, probably at least that actually. Now let's just say that their gateway went down and they couldn't access their database. They couldn't access the client files, which are all in the cloud. And so you get a phone call, you race out there, you discover that the gateway has failed, and you quickly install a new one, you bolt it into the rack, you download the configuration, and up and running again. Let's just say you got all that done in an hour. So it's pretty quick turnaround, all up and running in an hour. Well, that particular accounting firm, if they're charging out on average of $200 an hour per person, that hour of downtime has just cost them $10,000, hasn't it? Okay, $10,000. So maybe we need to think of a better solution. Okay, what about if a business like that was not conveniently located in the CBD, in a city where the support was readily available, or didn't have a support person on staff that could rush out and change that over? What if they were located maybe up in the north of, or in a remote area? Let's say they were in Australia, up in Cairns, maybe, up in the north, up in Cape York. And it was going to take you a day to get up there and change that gateway over and load that new configuration. And nobody else knew how to do it. No one locally knew how to do it. Well, that's a whole different scenario. So, yes, you could keep a spare one in the cupboard, but there is a better way. There is a better way of dealing with that issue. So, that better way is clustering. So, we're going to talk about clustering, high availability, and just remembering that the concept of high availability is to really make sure that we identify these things called single points of failure and we eliminate them. That's really our goal, so that if something fails, we don't lose services, which is really the goal of high availability. So let's take a look at this idea of clustering and get into seeing exactly what this is, how does it work, what does it do. So we're going to describe high availability clustering functionality, name the chassis cluster components, and describe advanced chassis cluster topics. Alright, so an overview of high availability. So what do we get with a chassis cluster? So what are we talking about here? Well, we're talking about, instead of having your spare device in a cupboard, okay, and then quickly swap it over when the live one, or if the live one fails, you actually have your spare device bolted into the rack and clustered together with the live one, so you in fact have two live ones. Okay, so with both of them are live. And why do we do that? Well, because we reckon that the chances of both of them failing at the same time is fairly remote. Okay, that would be, you'd have to be really unlucky for that to happen. So what we're saying is that if we have two of them, then we're probably not going to have a situation where they both fail at once. And so the goal then is if one of them fails, then the other one immediately takes over the workload and can continue operating. So the end result is we don't lose any services. We don't lose connectivity, we don't lose connectivity to the cloud, we don't lose connectivity between our internal networks, everything keeps working. So that's the goal. That's what we're aiming to achieve. So what we get here is an active-passive control and active-active data plane. So what we're saying is that the control plane is active-passive. So we've got two devices. One of them is the active device from the control plane perspective. The other device the control plane is passive. It's kind of like a slave, like master-slave type situation, where it's just sort of being driven by the other device. But the data plane, which is where all the forwarding happens, that's the packet forwarding engines, both of those are active at the same time. So we can be forwarding traffic through one device and forwarding traffic through the other device at the same time. So really we can, and what's the advantage of that? Well, the advantage of that is we can load balance the traffic between the two devices. So instead of just having one sitting there doing nothing until the other one dies, and then it becomes live, fails over, they're actually both forwarding traffic. So you actually are getting the benefit of the combined bandwidth of both devices as well. Okay, so you're actually getting a benefit by having them both in there and working. So what we're saying is that the routing engine or the control plane, only one of those is active, so we're only really configuring one, and what we're saying is that those configurations are then mirrored across onto the other one. But the routing engines, or both of them, are active and forwarding traffic. So we get a stateful session failover. Now you will remember that with our firewalls, we have sessions, right? This is a stateful firewall. So we are keeping a track of sessions, keeping a track of outbound traffic, inbound traffic, and the security policies around that traffic. So we have got a session table that records all this information. So what we're saying is that if a device fails in our cluster, then we will have a failover to the other device. So the other device will immediately take the live role, and we will fail over our network address translation, we will fail over our application layer gateways. If we have IPsec tunnels set up, they will fail over to the other device as well. All of our authentication. So of course what that means also is that all of our policies, all of our zones, all those things that control the security access to different parts of our network, security access from outside of our network to inside of our network, all of those things are going to fail over. Okay, so this is not just something like virtual router redundancy protocol, where all we're doing is trying to switch routing from one device to another. No, we're not doing that. We are failing over the entire security mechanisms that we have put in place, all of our policies, all of our zones, all of our network address translation, our VPNs, all of that, okay, which is configured on a gateway, will fail over to the other device if one of them fails. Okay, so it's our entire security configuration that's going to fail over. So what we are synchronizing is the configuration. What does that mean? That means that if you go onto your active control plane and make a configuration change, that change will be synchronized across to the passive control plane. So that if you fail over to that control plane, the configuration is live. So it's totally live, totally synchronized between the two devices. And the session state. Okay, so the state of the session, in other words, the contents of the session table is mirrored between the devices. So each device has got an identical session table mirrored between the two devices. Okay, so let's take a look at sort of getting into the detail of this. So within a cluster, we've got two devices in our cluster. So there's a maximum 2 devices. Well, you've got to have 2 devices, but you only have 2. And pretty much they've got to be identical. I mean, I'll just say that. Okay, they've got to be same model, same hardware, same interfaces, pretty much the same everything. So the the best approach to this clustering concept is that from day one, when we are setting up our gateway, we decide we're going to build a cluster. That's the best approach to the whole concept of clustering. Because then, of course, you just buy, instead of just buying one SRX, you buy two, right? That's it. Simple as that. Well, gee, now I've got to buy two. Yes, but what would it cost you to lose your network connectivity? Right? That's the question. Probably a whole lot more than the cost of the other device. So you buy two, you get two of them. They've got to be the same, so basically the same everything. I'll just say, just get two identical devices, right? That's the best way to go. Okay, so we've got a couple of important links that go in between. We've got a control link and we've got a data link. Okay, so we are passing control information and we're passing data information. You'll notice that the other forwarding plane can be active or can be passive. We'll talk about how to configure it so that it is in fact active. Alright, so let's look at the components of our cluster. There's a few things that we need to look at, a few things we need to configure and set up so this will work. We have got clustered devices. They're grouped by a cluster ID. So every cluster has got an ID. The nodes within a cluster are identified by a node ID. And we create these things called redundancy groups. I'm going to come back to that concept of redundancy groups. A redundancy group does not mean, it's not the same thing as a cluster. Okay? A cluster is two devices configured as a chassis cluster, but a redundancy group, we'll get back to that. I just want to kind of leave that concept for now. We'll come back to sort of what these things are and how they work. But we've got some interfaces that are specifically used to make the cluster work. We've got this FXP1, which is a control link, and that is the link between the two routing engines. So what does that do? Well, when I go into my active device and I make a configuration change, that configuration change is transferred across the control link to the other device. We've also got other control information like session table information, all that stuff that is live and running and controlling the operations of the sessions are all mirrored across that link. We've got a management interface, FXP0. Now that particular name, FXP0, is the standard name for management interfaces within Juniper devices. Now some devices have got a separate interface that you plug a cable into and then connect to manage the device. So it would be have an Ethernet port on it, for example, and you hook that up onto your network, and that becomes your managed interface, and the only thing you ever use it for is to connect to the device to manage it. Now here's the thing, some devices don't have those, like the devices we're using, for example, our SRX devices. It doesn't have an FXP interface on it, so there is no designated port for managing the device. However, when you form a cluster, suddenly an FXP interface will appear. Okay, now what's happened? Well, what's happened is one of the interfaces that we would maybe normally use for forwarding traffic has been grabbed and is now designated as a management interface. Okay, so you kind of lose. So if you don't have an FXP interface, then what happens is one of your regular interfaces, one of your regular Ethernet interfaces, is kind of is kind of grabbed by the clustering process and says, well, this is now your management interface, so we're going to be using that for that. So you kind of lose a forwarding interface, if you like, when you cluster. That's something you have to think about. On the high-end devices, you've got a designated FXP interface already. But on the lower-end device, you don't have one. But when you cluster, okay, you're going to lose one of those. So just have to kind of bear that in mind when you think about how many interfaces do I need. We have this fab interface here, which is the data link, and that synchronizes our forwarding planes. So that's all the synchronizing data goes across the forwarding plane. We have this thing called an SW fab link, and what that does, that will pass network traffic between the devices. So where you've got traffic that maybe comes in on one device and has to go across onto the other device, that's the link that transports the actual flow of traffic between the devices. And we have this other thing called a wreath, which really is a redundant Ethernet. That's what the RETH stands for. So a wreath interface, as we'll see shortly, what that is, it's a pretty logical interface, sort of called a pseudo interface. And what the cluster does is it grabs a traffic forwarding interface off one of the nodes and grabs a traffic forwarding interface off another node and then puts them together to create this wreath interface, which is more of a logical interface, but the components of it are these two physical interfaces, one from each node. Okay, and the purpose of that is, of course, the failover. So if we lose one node, we've got the other one is attached. So this quite a conceptual, well, it's a logical interface in many ways. Okay, so let's have a look at how setting up the cluster ID. So we can set up a cluster ID value between 1 and 15. Kind of means you can have 15 clusters on your network. Device can only belong to one cluster at a time. If the cluster ID is 0, then the software ignores the high available configuration. And then a device within a cluster is identified by a node ID. So we've got a cluster ID, and we've got a node ID. And of course, there's only ever 2 nodes in a cluster, so the node ID is either going to be 0 or is going to be 1. So either node 0 or node 1. Okay, so once you are in the process of creating a cluster, you have to reboot the device. So as soon as you get your 2 devices, okay, let's form a cluster, then you have to reboot them, and then they come back up in cluster mode. I would say that if the other side of that is that if you have a device that's been in a cluster and now you want to get it out of cluster mode, then you have to go and delete the chassis cluster and then reboot it and come out of cluster mode. Okay, so we have to so we go and use the command set chassis cluster ID, so ID 1 node 0, and that device then becomes node 0 in cluster ID 1, and then of course you go to the other device and you'll make it node 1 in that cluster. Okay, so what have we discovered? We discovered we have a cluster ID and a node ID. Okay, node ID identifies general security device within a cluster, and it's either 0 or it's 1. So again, set chassis cluster ID, node ID reboot. So essentially set one of the devices as node 0 and the other device becomes node 1 within the same cluster ID. Okay. All right, let's talk about this concept of redundancy group. There is a special redundancy group which is called redundancy group 0. And then we have 1 through to 255, which are kind of user configurable redundancy groups. And really the point of this redundancy group is it's a logical construct which sits within the cluster. And what we get to do with it is we get to associate these reef interfaces with a particular redundancy group. And we use this concept for load balancing. So what we do is within a redundancy group, one of the devices in the cluster will be the primary device and the other will be the secondary. So in other words, one will be actively forwarding traffic and the other will be the failover. And what we can do is we can create our cluster. We can create a couple of different redundancy groups, so redundancy group 1 and redundancy group 2 in our cluster. And we can, within our redundancy groups, we can have one device being active and the other being passive. And on the other redundancy group, we can have it the other way around, have it the opposite. So the one that was passive on, say, group 1 is active on group 2. So what we get to do with that is we essentially get to load balance traffic across the device between the different networks that may be connecting to the device. We'll get a look at that in some detail shortly. So these redundancy groups are a kind of a logical construct that we create on the cluster, and what we get to do with it, as I said, we get to put interfaces into this redundancy group. So it really represents, as you see on the slide here, a group of redundant interfaces. Okay. Redundancy group object state. So the object can be one of the following three states: blank or starting, primary state or secondary state. So we can basically change from those different states. And so they change between those different states. So within a redundancy group, just go back and take a look at that slide there, we have got a device is either starting up, or it's a primary, or it's a secondary device. So primary means it's active. Okay, so primacy determination is as follows. A node priority ranges from 1 to 254, so you can set a priority on a node within a redundancy group. The higher number is better. Both nodes initialize at the same time with an equal node priority, then node 0 becomes the primary. Okay, so unless you change the node priority, node 0 becomes a primary. If they initialize at different times, the node that comes up first becomes a primary. So if you power up node 1 first, then it will become primary. Now, the primary node, whichever one it is, will remain the primary node unless you configure preempt for the redundancy group. So by default, the primary node will stay primary. So it won't, if you say have a high priority on node 0, but you boot up node 1 first, you won't get a failover just because node 0 comes online, unless you configure preempt option for the group. Okay, so physical interface monitoring triggers a redundancy group state transition. So what we're looking for is an interface failure, essentially. An interface goes down. Because if the whole device fails, the interface will of course go down. So the interface associated with the redundancy group 1, for example, receives a weight value, and redundancy group 1 has an initial threshold tolerance of 255. If an interface goes down, the threshold equals the threshold minus the interface weight. If the threshold value will reach 0, the failover to the other node triggers. So these are configurable parameters. You can configure the threshold, you can configure the weight of a particular interface, and then that will determine what happens if that interface fails. Okay, so this is an example of using a couple of different redundancy groups. RG0 is reserved. It's reserved really for the cluster itself. There are values from 1 through to 255 which are configurable by the user. And in this case, we have got redundancy group 1, and we've put reef 1 into redundancy group 1. We've got redundancy group 2, we put reef 2 into redundancy group 2. And what we're doing with it is, for redundancy group 1, we've got one of the devices being active, the other passive, and for redundancy group 2, we've got it the other way around. So what we are in fact doing is using the forwarding plane of both of the devices to forward traffic. So one of the networks, in this case we've got 10.10.0016 network, that's forwarding traffic through one of the devices, and 10.20.0016 is forwarding traffic to the other device. So they are both, the forwarding plane of both devices is in fact active. Even so, the control plane will only be active on one of the devices. So even though the forwarding plane is active on both. And that is configured using redundancy groups, and it's simply setting up the which node is going to be primary. And you can do that by using the priority numbers. Okay, so you go into redundancy group 1, set one of the nodes with a higher priority, and that will become the primary, and you can go into redundancy group 2 and set the other node with a higher priority, and that will become active in redundancy group 2. And what it means is that you've got this reef interface here where you've got your configuration is attached to, but the reef interface has got a couple of physical interfaces which are the child interfaces, and depending on the primacy of the nodes will determine which child interface is actually passing the traffic within the reef group. So you can load balance by simply having a couple of different redundancy groups and having one node primary in one and the other node primary in the other. Okay, let's take a look at these interfaces. These are redundant Ethernet interfaces. When you create a cluster, you will see appear within your cluster these new pseudo interfaces called a reef. And what they do is they bundle together a couple of physical interfaces, which are the child interfaces of reef, one from each member of the cluster. So these member interfaces then inherit their properties of the reef as configured by the user. So here's the thing. You don't configure the physical interfaces, you configure the reef. So if I'm putting an IP address onto an interface, I'm putting it on the reef interface, I'm not putting it on each of the underlying child interfaces. So What does that mean? That means that your configuration doesn't say GP 001. It doesn't. It says, it actually references a wreath interface, so it has a different name. Okay, so what that means is that if we're going to be applying a configuration to a cluster, the interface names in our configuration are different to what they would be if we didn't have a cluster. Okay, so what that kind of means is you can't decide one day, oh, I think I'll take my gateway and make a cluster. Let's add another one in, and let's just load the same configuration that I had before. It won't work because your interfaces are now wreath interfaces, and you need to be referencing those things in your configuration. Okay, so if you did want to do that, you would have to edit your configuration offline. So you save it, open it, change the names of the interfaces, make sure that you kind of know what you're doing with them, and then save it back on, and then you should be good to go as to whether they will be active or passive. The failover properties of the member interfaces come from the router group configuration. So that's all configured in the router group itself. And the wreath interface has a virtual MAC address. So it's based on the cluster and the interface ID. So the cluster comes up with a virtual MAC address and applies it to the wreath interface. So it is, as you can see, it is really a virtual interface that consists of these two physical interfaces. Okay, you can, this is the MAC address of the virtual MAC address here. So you can take a look at what that is. Here it is, wreath. Show interface is wreath 0. So you see the name of the interface. Okay, wreath 0. So we're not talking about GE 0/0/ whatever. We're talking about a name which is wreath 0. I'm just taking a look at the MAC address there. Okay, now, so we've talked about, let's go back here, we've talked about wreath interfaces. Wreath interfaces are the physical interface from each node. So we've got redundancy there, right? We've got redundancy built in to this wreath interfaces. But what would happen if we wanted to create a lag group? And what's a lag group? Remember back to the CCNA course, way back then, we had this thing called an ether channel. Remember that? Where we took an interface, we already talked about a switch, so we took a couple of interfaces on a switch, bundled them together, and they acted like one interface. And we kind of got the combined bandwidth of all those interfaces together. The other thing we got with that concept was that if one of the interfaces went down, the other ones kept working, right? So we didn't actually lose our link if one of them went down. Well, we can take these wreath interfaces and we can combine wreath interfaces together into a wreath lag group. So what we get is the combined bandwidth of the two wreath interfaces. Well, we also kind of get double redundancy as well, so that if some of the channels fail, well, we've really now got, so we take a couple of wreaths, bundle them together, we've really kind of got 4 physical interfaces now involved in this process. Only 2 of them are active, but we've still got this built-in failover as well. Additional built-in failover. 2 layers of redundancy. So the child interfaces must be the same speed and operate in full duplex mode, which is good. Fiber and copper cable types can be combined. So here we are. Combine those, no problem. Maximum of 128 lag interfaces. Okay, so what we're saying is we can have 16 member interfaces on an 8 per node per wreath lag. And the LACP protocol is supported. Link aggregation, so link aggregation control protocol. We can set the minimum links, and we can have local flags, which are also supported. Okay, so let's take a look at interconnecting switches and reflags. So there we've got a couple of reflag interfaces. We've got our switch down there on the bottom. So we have to have 802.3AD enabled on the switch, which is basically the link aggregation control protocol enabled on those particular switch ports, and they will then be bundled into a lag group. Lag groups must be configured on the switch. Single terminating switch configurations require 2 separate lag groups on the switch per reflag. Okay, so we've got 2 separate ports. So we've got a lag here of a couple of different reef interfaces. We've got 4 ports involved in that process. And a single terminating switch configuration requires 2 separate lag groups on the switch. Okay, so just the point there, stand back, is that yes, we can take our redundant interfaces and combine them together to make a lag group out of our redundant interfaces to get kind of double redundancy and increase bandwidth. Alright, so let's take a look at this FXP interface used for out of band management. What does that mean? Out of band, what does that term mean? Again, out of band. Common telecommunications term actually. Out of band. What's an out of band interface? Out of band interface. Heard that term before? Out of band. It simply means that that interface is not used for transit traffic. It's only used to manage the device itself. So the only purpose of that interface is to connect to the device itself and to manage the device. Okay, you can. In fact, it's quite common in a large infrastructure to have an entire out-of-band network. It's a whole separate network that is purely used to manage the devices in the network. Okay, so it's used for out-of-band management, dedicated port on the high-end device. So what we're saying is the high-end devices have this physical port built into them, which is the FXP port, into which you plug a Cat5 cable as the usual thing, and then that is then connected to your management network and you manage the device. But on the branch devices like we are using, what happens is it grabs what we call a revenue port. Now, a revenue port is just a name for a regular, everyday port that you would normally use for transit traffic. So, kind of called a revenue port. And we just grab one of those and say, well, that's now your FXP interface. Okay, and that underlying interface is no longer available for anything else. It allows access to each node of a cluster, so you give each node a unique IP address for the FXP interface. So you're going to require a couple of IP addresses, which you would have had anyway if you had 2, but you give them a different IP address so you know which node you are connecting to when you're managing it. We'll note here that it requires the group's configuration statement. We'll have a look at that once we get into how to configure these devices. Okay, we have a the first of our chassis cluster interfaces. This interface, the FXP1 interface, is created when you create a cluster. It's used to achieve the clustering. We need a few different interfaces that we're going to use to actually achieve a clustering and support clustering. This one, the FXP1 interface, is a control link for the cluster. On the high-end devices, we will use a SPC port, which is a services processing port. It's a special card that is used on the on high-end devices, and we will connect our two devices together using this particular port type. However, on the branch device, we get to use a revenue port. So you've lost another revenue port, okay, when you cluster on the low-end device. So we're going to use up a few ports here. So that's something to bear in mind when if you're planning a cluster and you're using branch devices, which probably you are, right? You're quite likely that you're using a branch device. Think about how many interfaces do I need to actually connect to my network, because when I form a cluster, I'm going to lose one for my management interface. I'm going to lose another interface just right here, FXP1, okay, which is going to be used to connect my devices together for clustering. So I've lost two of my regular interfaces already just to support my cluster. I can't use those for transit traffic. I can't hook those up to my network. Right? They're just there to make the cluster work. This enables the configuration synchronization. So when we do a configuration change in our active control plane, it will mirror that configuration across onto the passive. Also, we use these heartbeat signals to determine the health of the control link. So we want to make sure that the control link is up and running. If we lose that particular interface, just so that interface went down, could happen. Well, our cluster is no longer a cluster. We've essentially lost synchronization. So we need to know if that happens. We can configure a threshold on that, and if that interface reaches the threshold, then we will conclude that our cluster has gone down. Primary node, the RG0 becomes a primary node, and the secondary node is disabled. To resume the operation, we must reboot the disabled node either by using it manually or by using the control link recovery configuration. Okay, so we have this other interface, which is a FAB-N interface. Now, on a branch device, we're most likely going to use just one interface for this, although you can use more than one interface for this particular link. If you want to have more than one, you can have multiple interfaces. But we have two interfaces, one for each device, used for high availability data plane fabric link. And again, so what this is another interface that has been grabbed and used for the cluster. So far we've grabbed three separate interfaces that we're just using to support the cluster. So there's three interfaces that you can't connect to your network, right, and use for your transit traffic. Like I said, you've got to sort of plan it. You've got enough interfaces left over to do what you need to do. Enable session synchronization and transit traffic link for the active data plane. So that's where this is at. Monitored using fabric probe. So with GNOS operating system disables one node if the fabric fault occurs. Kind of like the control link failure thing. If the link goes down, you've got to reboot the other device to get the cluster back up. Can't put filters on it. We've got this dedicated, we've got another interface which has been grabbed by the cluster. to just make the cluster work. Okay, now we've got yet another interface, which is the SW fab, and then we give it a number. So this is another interface from each device, used for high availability switching a fabric link, and we must use interfaces that support Ethernet switching. Cluster node must be connected back to back and enable switching for layer 2 Ethernet traffic between the cluster nodes. Okay, so there's another interface that we've lost. Okay, so far we've lost a management interface. We've got monitor and control plane. We've got one for our forwarding plane and one for switching. So there's 4 interfaces that are being used just to support our cluster. Okay. So if we've got a device that, say, typically may have 8 interfaces, say our little SRX 100s with their 8 interfaces, then you've lost half of it when you cluster. And then you've got 4 left for transit traffic. It's just something to bear in mind. Alrighty. So we don't support filters, policies, logical interfaces, or services, but we do support jumbo frames on that particular interface. Alrighty. Now, we can actually have redundancy in our data plane and fab and SW fab link. So where I said you've lost one interface, we can decide to put more than one interface into this link and have redundancy in the link itself, which supports the cluster. So you that's optional. Kind of depends how many spare interfaces you've got. If you're using maybe a larger device, maybe an SRX240 where you've got 16 ports, and you think, well, I don't need all of those. I'll put another link in, put some redundancy into my cluster. Why not? You've got the spare interface. Why not do it? Okay, so you can load balance this interface, and we'll have the certain traffic traversing one link and the data traffic traversing the other link. You can load balance the SW fab interfaces as well, and use an internal aggregate Ethernet interface for that. Okay, on the high-end devices, you get the dual control plane links as well. You don't get that on the low-end devices, on the branch devices. So, on the higher devices, you can. Okay, so provide session or flow redundancy. The data plane synchronizes the state by sending these special payload packets named real-time objects across the fab interface. Real-time objects ensure consistency and stability of sessions if a failover occurs, and RTO traffic has a higher transmission priority than transit traffic. So RTO creation is dynamic in memory, so we'll be actually sending the session table entries and IPsec security associations. Example of what that link is used for. Okay, so what we're doing is we're ultimately, we've got these 2 devices. They're completely synchronized. We've got traffic going between the control plane, traffic going between the forwarding planes to sync everything together. We've got the ability to send transit traffic from one device across to the other device across these forwarding plane links as well. And also we've got the ability to send layer 2 traffic across the SW fab link. Okay, so let's take a look at the interfaces. Summary of the interfaces. We've got node 0, node 1. We've got FXP0, which is the link between our control planes. We have got Fab N, which if we only had one, we just call it Fab 1, and SW Fab 1, for example, which is the link between our data planes, there are forwarding planes. We then create these wreath interfaces, which really is a combination of two physical interfaces, one from each device, which form our child interfaces. One for each device is our child interfaces. They combine together to form what's called a wreath interface. So you have wreath 0, wreath 1, wreath 2, etc. And we've got our management interface, the FXP0 interface, which is our management interface. So this is kind of all happens when we create a cluster. Okay, all these new interfaces appear, and suddenly we start to use all these new interface types. Okay, so like I said, you can't just take your old configuration and throw it back onto your cluster. You've got to rethink where all this, where your active interfaces are going to be, because your active interfaces, your actual transit interfaces, will become wreath interfaces. So what we call GE000, they'll be called wreath 0, wreath 1, wreath 2, etc. Okay. Alrighty, so that's the basics of forming a cluster. Let's take a look at some. Actually, just go back to this here. So which interface becomes FXP0 is determined by the model of the device that you're doing it on. Ours is going to be GE000. We will find that GE000 will suddenly become FXP0 when you form a cluster. The interface that is used for FXP1 is predetermined. You don't get to configure that depending on the device. So, for example, on an SRX100, it becomes the FE007 interface is the one that's grabbed and used for that. You do get some choice over these other interfaces as to which one you're going to use. So some of them you don't get a choice. Some of them are just grabbed and say that's it. That's now I'm going to use this for my cluster. And some of them you do get a choice. The point is though, you've got to have those connections between the two nodes. Usually what you've got is your rack. You've got two nodes in the rack, and these interfaces are just connected back to back between the two nodes. Generally the way you do it. Okay. Alright, so advanced topics, let's look at these advanced topics. Latitude deployment. So what we're saying is that normally you've got these back to back in the rack, but you don't have to. You can have them in separate locations, like your two nodes, one node in one rack somewhere, and another node in another rack somewhere else. If you do that, a few requirements here. FXP and FAB interfaces. Latency is going to be less than 100 milliseconds between the nodes. Bandwidth got to be at least 1 gig on the path, and no other host should be able to send or receive traffic on the networks where the control and data links reside. Redundant networks, control and data links should traverse two separate physical paths and two separate switch topologies. Okay, so physically segregated switch topology, control and traffic links are not intermingled. No single device failure would cause a split brain situation. Split brain means that we've lost one of our links, and what happens is you get a situation where both of the devices think that they're the primary device. So if you lose both links, then you can have a situation where each device thinks, oh, I must be the primary because I can't contact the other one, so I must be the primary. But if you just lose either one of the links, then that situation never occurs. And use VLANs to separate the traffic from all other traffic. So you can actually have them going across a WAN. In which case we're going to need a layer 2 VPN. We can use either circuit cross connect or some kind of perhaps MPLS network in there. We can use VPLS, which actually runs on an MPLS backbone. So, Ethernet switching in a chassis cluster supported all branch devices except SRX 100s, 110s and 210s, and we can use the family Ethernet switching, only supported for local interface. So that's just some of the limitations on Ethernet switching for these devices. Pairing a cluster for layer 2 switching, we create the interconnecting SW-FAB interface before configuring local interfaces for Ethernet switching. Must use switching enable interfaces, and there's some model specific information there, and some of the other protocols and whatnot that we need to consider. That's just looking at our Ethernet switching status. Okay, that's looking at the fabric link. So show chassis cluster Ethernet switching stats. We can take a look at that. Okay, monitoring mode addressing for redundancy group failover. What we can do here is we can set up our cluster to monitor a reachability to a particular IP address. And if we lose reachability, then that can trigger a failover. So what we're saying is that if we've got, say, one of the nodes connected to an upstream gateway and the other node connected to a different upstream gateway, and we've actually sort of load balancing our Ethernet connections, if one of our internet connections drops, we can fail over to the other node. This is the configuration parameters here. So we've got the IP monitoring, we've got global weight, global thresholds, retry intervals, retry counts, they're the default values. If we're monitoring multiple addresses, so here we're monitoring, in this case, 1.1.1.1 and this 172.20.30.2. If we're monitoring a second address, then they have to be identical. Now we can look at the status of our addresses. So what happens is that if we lose reachability to one of our addresses that we are monitoring, then that can trigger a failover to the other node, which is attached to the other reachable address. IPsec tunnel termination. So we have a single node terminates the tunnel. The root interface address is typically used as the anchor point. The backup node is ready to take control. The keys and session information are synchronized, and the IPsec and IK security associations are preserved. So you can fail over to the other node, and your IPsec tunnel will be preserved. IPv6 clustering, so that it is supported, so pretty much the same things that are supported. The only thing that's unsupported at this point is the IPsec site-to-site VPN over IPv6. It's not supported on the cluster at this stage. Okay, state synchronization on the high-end devices. We use special interfaces which are not available on the low-end devices. These SPU interfaces are used to connect the devices together and support clustering. As I said, on the low-end devices, you simply grab a regular interface, and that's going to be used for that. With the routing protocols, We have a graceful restart will be used to switch the routing protocols from the active node across to the passive node. So essentially, you don't have to signal that you've lost connectivity to a device or to the device as part of failover. So we have a graceful restart on the routing protocols. And we want to cover this before when we looked at our routing specifically, but essentially what that means is that while a failover is occurring, you don't lose routing connectivity. The other devices on the network don't say, hey, I've lost my router, and have to reconfigure their protocols or reconfigure the network. Okay, so we had a look at high availability clustering functionality, looked at chassis cluster components and discussed advanced topics. What we're going to do next after the break is we'll come in and look at how to actually configure the actual configuration of the cluster. And we'll go through that, and I'll sort of talk about some of the issues around configuring the cluster. But some of the review questions: which interfaces do the control and data planes use? So to create the cluster, okay, on the control plane, we've got an FXP1 interface which synchronizes the control plane. We have a FAB1 or whatever number we want to give it interface that controls the data plane. And we also have an SW FAB interface that controls layer 2 traffic between the data planes. What is a routing group? What is the significance of RG0 and RGX? Okay, so we saw that a routing group is a logical construct within the cluster. RG0 is reserved to identify the cluster itself, not like the hardware there. Whereas RGs 1 to 255 are user configurable, and what you do is when you create a cluster, RG0 exists. It's there. It's already created as part of the process. But then what you do is you go and create your user configurable routing group, and the point of a routing group is that you will put interfaces into a routing group. Okay? And what you then do is, within a routing group, one of the nodes in the cluster will become primary, or will be designated as primary. The other will be designated as secondary. What that means is that the child interface in the wreath group of the primary node will be passing traffic, but on the secondary mode will not be passing traffic. Okay, so the active forwarding plane will be on the primary node. So what you can do is, if you've got multiple networks that you are servicing, you can create multiple routing groups, and you can configure interfaces to connect to different networks on the different routing groups, and you can have one node being primary on one group and the other node being primary in the other group. So you in actual fact are load balancing the traffic between the different networks as they traverse your cluster. So you are in fact getting the bandwidth benefits of both devices in the cluster. Okay, default threshold for interface and IP monitoring. Well, the default threshold is 0 and the default value is 255. So basically what that means is that if you lose an interface, you get a failover on it because the threshold drops to 0. That's basically what that means. Okay, we will take a break, and when we come back, we're going to take a look at how we configure a cluster and go through the actual configuration process.